Hi class, this is Professor White. I wanted to catch up on a few things that we missed for Unit 7, Lecture 3. So this is a PDF lecture, so I'm just going to try to annotate what I'm saying here in this Jupyter Notebook. So we left off wanting to know about what sample covariance is. So we had learned about covariance, but now we're going to learn a little bit about sample covariance. So recall that covariance is a property of random variables. Sample variance is something about samples, namely data, right? So covariance is a concept that we associate with probabilities and random variables, and sample covariance is something we associate with having data. So we compute it only when we have data. So we saw that there's a connection between expected value and median and mean. So recall that with the law of large numbers, that if you take a lot of data and you compute the expected value, if you take a lot of data and compute the mean, it should be the same as the expected value if you knew the underlying distribution. So we can see an example, why not? So let's take some data, okay, and we'll compute the mean of it. So I'm going to take data which I know is coming from a probability distribution. So I'm going to rely on NumPy, which has a random value function. Let's see if I can get it. So if I take random, noise normal. So I'm going to generate some normally distributed data, and I'm going to say that its mean is, say, 3.5. Okay, so I'm going to just grab some data like that. And here's my data. Okay, so we have a few values here. So 2.5, 4.6. Now I know the expected value is 3.5 because I am generating this data from a known normal distribution. So just recall that this distribution is the normal distribution, so it's 1 over the square root 2 pi sigma squared times e to the x minus mu squared 2 sigma. Okay, so that's the distribution. So I generated random data from it with a 3.5 mean. Okay, so 3.5 expected values. So let's take a look what the mean is for that data. So the mean is 3.4. Okay, and we know the expected value is 3.5. So the law of large numbers says that as we generate more and more data, that should match the expected value. So here is 10 data points. Let's try 100 data points. Okay, let's try 1,000 data points. See, it's getting there. So notice that when I execute the cells, it changes a little bit because we have a new set of 1,000 points. And let's try 100,000. Okay. Now we're getting real close to that. All right. So as the number of values increases, law of large numbers says that these statistics, like median and mean, will match their random variable or probability equivalents like the expected value. Okay, so that was just a little detour on law of large numbers, but let's get back to the sample covariance. All right, so let's define sample covariance. So sample covariance is how two types of data vary. Okay, so it's how two types of data vary. Again, we can have things positively or negatively covariating. Okay, but data, we have to know the data come from same sample space. Okay, so this gets into this subtlety that we've talked about a little bit in the class, is the difference between sample space and random variables. Okay, so let's see some examples. This will help this make more sense. So let's think about the sample space first. One sample space we use a lot in this class is weather. So sample space is weather. And let's define the weather as, say, a product sample space. So we have maybe Q of temperature, we have Q of maybe precipitation amount, and maybe Q of, I don't know, the wind, all right? So then we have these combined. So the Q of weather equals these three things out of product. Is it two T's? I always get confused. Nope, those would be otters. Huh. Maybe this is not the LaTeX symbol? Outer. Pretty sure it's outer. Alright, well, I'm going to put an X here, guys, and we'll just know that it's an outer product. Okay, so let's see some examples of the sample space. So here is an element in sample space. So here's an element. That would be like maybe we have 45 degrees, and then we have 3 inches of snow, and we have 41 or 4 mile/per-hour winds. Okay, that's an example of the element. But let's see what examples of paired data is that we can compute sample covariance. So I could compute sample covariance of, say, the weather and precipitation. So here's data for my sample covariance. So I could have, maybe 45 Fahrenheit and 3 inches of precipitation. Then I could have maybe 22 or 33 Fahrenheit and 2 inches of precipitation, maybe 31 Fahrenheit and 12 inches of precipitation. So these are examples of data that's paired that I can compute sample covariance with. Okay. Now let's see an invalid example. So here's an example of some data which doesn't exist in the same sample space. Let's say I look at maybe precipitation on Monday, or on a day of the week, and then total precipitation for the week. Then I look at precipitation for another day of the week, like 2 inches, and then I look at total precipitation for the week. Now these aren't really connected because they're not really in the same sample space, right? So the precipitation in the week is sort of something that we observe, per week. And then this is something we observe per day. So like it's unclear what exactly the sample space or what an element of the sample space would look like. And you could do something like this is precipitation today, and here's for the last 7 days. That's totally valid, but saying this is for the course of the week and this is 1 day of the week, that's not valid. All right. So what is the actual formula? Let's put this down. So this is precipitation. Oh boy, I really tricked myself. Precipitation. Just a second, guys, here. Precipitation. That's what we want. All right. So what is the actual formula? So what is the formula for sample covariance? So the formula is written like this. So remember we use sort of a subscript here, like sigma sub x or sigma sub xy. That means that it's about data. Okay. So if it has this underscore x or y or something, that's like a clue to you that it's about data. Notice this is the same thing we had for standard deviation, but standard deviation was sigma underscore x. So here, this sample covariance is sigma underscore xy. All right. It's 1 over n minus 1. And this is very akin to what we saw for the equation for sample variance. Sum from I to n. We have x minus x bar, y minus y bar. And recall that bar x is sample. So this is the equation for sample covariance. Now, remember that we had, for variance, we had n minus 1 as well. And So sample covariance also has the same. And actually, maybe it'd be useful to recall the equation. So compare with sample variance equation. So the sample variance equation is written like this. Okay, so you sort of see the connection. So you can imagine that if you would write out, and this is true, that sigma x is equal to sigma x squared. So the sample covariance of x with itself is the same thing as the sample variance. See that? Like if you had y here being x, it would be the same. All right. So one of the things about computing sample covariance is that you can see there's sort of you can have a sigma x, a sigma y x, a sigma x x, and if you had 3 random variables, you might have sigma x y z, sigma y x z, and you can change them around. Like if I swap x and y, it's the same quantity because this is a product of these two things. So we usually view sample covariance as a matrix of a bunch of random variables. So let me show you an example. Is that you might we will talk about sample covariance matrix. So in the case of 2 random variables, this is not that relevant, but we'll just take a look for 2 random variables. We would have sigma x, sigma x, y, sigma y, x, sigma y, y. Oops, to end it. So here you can see that there's kind of a nice matrix way of representing it. So we have the sample covariance of x with itself, the sample covariance of x with y, then with y with x. Obviously, this matrix is symmetric. And also note that this here is the sample variance of the x random variable, and this is the sample variance of the y random variable. So this idea can be extended out to further dimensions. So if we wanted to have 3 random variables, we'd have sigma x z, then we would have these y's, right, so we could have with 3 random variables matrix. So we're going to talk a lot about sample covariance matrices, because that's sort of how you represent these things and compute them, and that's how we'll do it in NumPy. The last thing is there's something called sample correlation. So one of the things about covariance is that covariance includes information about how the random variable varies, or the 2 random variables vary. So if x and y move the same direction, the sample covariance is positive. If they move opposite directions, the sample covariance is negative, like we saw in the covariance lecture. But the actual magnitude of this number, of the sample covariance, it includes information about how much these things vary. So for example, in here, the sample covariance will change if we go from Fahrenheit to Celsius, right? So if we want the sample covariance to tell us about the relationship between 2 numbers, 2 random variables, we don't really want it to be sensitive to the units, right? Like if I want to know the relationship between temperature and precipitation, I don't care if you measure precipitation in centimeters or inches or the temperature in Celsius or Fahrenheit. I care more about the relationship between the 2 random variables. And that's where sample correlation comes in. Sample correlation removes this relationship between the 2 random variables and only looks at how their motion or how their movement is connected. So it's a very simple equation. So the correlation between x and y is going to be the sample covariance divided by the standard deviation of each number. So this here is the sample standard deviation, but obviously we could write it down as something like this. So I just am going to put it like this. What do we do here? One more? Yeah. So this is equivalent to the first definition I wrote. So it's like taking the sample covariance and comparing, and then normalizing by how the two random variables vary themselves. So one of the properties of sample covariance, one of the properties of covariance, or sample covariance, is that this is true. Oops, what do we do? That the sample covariance is always going to be less than the individual covariances multiplied by each other and then taking the square root. So because of this consequence, the sample correlation is going to have a really nice property that it's always going to be between -1 and 1. So the sample correlation is always between -1 and 1. And that gives us a really nice understanding that if two random variables are perfectly correlated, their correlation will have a magnitude of 1, and it will be 1 if they go up together, and -1 if they go in opposite directions. That is, one goes down, the other goes up, or one goes up, the other goes down. So that's the idea of sample correlation, is it removes this relationship. Now, of course, that means that we will have something called a sample correlation matrix. But now, instead of sigmas, we have r's. So we have to replace this all with r's. And people typically omit the word correlation. Or sample. They'll usually say correlation matrix. And part of the reason why is just that people don't usually talk about correlation of random variables or with probabilities. People usually look at correlation with data. So now we'll have a sample correlation matrix. And when we move on to the next lecture about NumPy, we'll see that sample correlation matrices are really important when you look at data. One of the first things you'll do when you're looking at paired data is to look at the correlation to see if they're related. Okay, so to summarize, sample covariance is a concept which is connected to covariance via the law of large numbers, so sample covariance is with data. We still have the restriction like we had with covariance that when you look at data, it has to come from the same sample space. Okay, so we have paired data, but the data that's paired, they have to be coming from the same sample space. It doesn't mean they have to be the same units. They can be different units like in this example. It just means that when you observe one, you must have also observed the other. So I think in this weather example, it's nice that maybe we observe the weather, we look at temperature, precipitation, and wind. Now we didn't look at wind in our data, but if you were going to observe the weather, you would observe these 3 things, and we looked at 2 of them. You could obviously include wind in this as well, but the paired data I'm looking at here was temperature and precipitation. To give you a counterexample of something which is not valid is looking at the precipitation today and the precipitation for the total week. Because when you observe one, you don't necessarily observe the other. Right? If you look at it today, you don't necessarily know what it's going to be for the whole week. And then that's sample covariance. Then here's the equation for computing it. We'll see in the next lecture how to do that in NumPy. And notice that it's about data, right? So we have a sum over data points. And sample covariance is related to sample variance. If you look at the sample covariance of something with itself, it's the same as its sample variance. And this little subscript xy is to indicate that it's to do with data. We view them usually as matrices. Then if we want to remove the effect of the magnitude of the numbers, so if we want to remove like how if I change from Fahrenheit to Celsius, it changes the numbers, we can look at correlation. And sample correlation is usually looked at more often than sample covariance. So sample correlation is the fraction or the ratio of the sample covariance divided by the individual product of variances with a square root. And sample correlation is bound between -1 and 1. Then again, it's more often viewed as a matrix. Okay, thank you guys.